Hey everyone, welcome back. In this lecture, we're going to learn about another kind of analytical solution, that is well equations. We're going to look at well equations for confined and unconfined aquifers, and later we're going to learn how to use these to analyze construction dewatering systems. So we're going to start out by looking at confined aquifers under steady state conditions. So there's another set of equations you can use to show how an aquifer responds over time to pumping, but in this case we're just looking at steady state conditions, so the effect of turning on the well has fully dissipated and we're in kind of a constant state associated with a given pumping rate. And so we're going to start with a confined aquifer, and so we have a well drilled all the way down to the base of the aquifer. It's screened completely through the aquifers. So this blue region is the aquifer. This tan region up here is an aquitard, or an impermeable layer. The dashed line represents the initial water table surface prior to pumping of the well. And then when you start pumping a well, the drawdown looks like this. We're just looking at one slice that goes right through the center of the well. If you imagine this in 3D, it's a cone shape. It's often called a cone of depression. It's centered on the well, and that line we're looking at here is the potentiometric surface. So if you were to so this is the saturated part down here, but that represents, if you were to drill, say, a monitoring well over here, this is the height to which water would rise. So it describes how the head down here in the confined aquifer varies as you go away from the center of the well. And so we're going to derive an equation to compute the flow rate to the well as a function of the hydraulic conductivity in the confined aquifer and certain boundary conditions. And we're also going to come up with an equation that describes the shape of this potentiometric surface, the water table, basically the shape of this cone of depression around the well. First of all, for our confined aquifer, we have some assumptions. We're assuming it's homogeneous, all the same material. The aquitard is impermeable. The thickness of the aquifer is constant, and it is of infinite lateral extent. The well fully penetrates the aquifer, as shown in the previous slide. The initial water table, the upper and lower boundaries of the layer are horizontal, and there's no head loss at the well. What that means is sometimes the material, the casing and stuff right around the well, there's some head loss required to get through it. We're ignoring that and just assuming it's a smooth transition we're down here in the aquifer, from the confined aquifer into the well. So using those assumptions, here are the variables that we're going to be working with. The thickness of the confined layer is D. The initial height of the water table prior to pumping is H. And the height after pumping is stabilized, HW describes the height of water inside the well. The elevation is basically the head in the well. R sub W is the radius of the well. That's typically quite small. R and H just mean at any point, it's some radius away from the well, R, you have a head H, and that is significant because we are going to derive an equation to define how that head small h varies as a function of R. We assume that the water flows perfectly horizontally to the well. And then this capital R up here, this is important. That is, if you pump this for a long time, there's theoretically some distance at which there's negligible drawdown. what do I mean by drawdown? This distance from the initial water table height down to the potentiometric surface is called drawdown, and inside the well is this distance down to the water table elevation in the well. At some point you don't have any drawdown, so the potentiometric surface is equal to the initial height head prior to pumping, and that capital R represents that distance, and it's called the radius of influence of the well. And later we'll talk about methodologies for calculating the radius of influence for a well. We're going to assume that Darcy's law is valid, so Q is equal to minus KIA, and I is dH dr. The hydraulic gradient is the change in head as a function of radius, so we're not dealing in terms of x or y here. This surface is symmetric around the well, so we use radial coordinates, and the hydraulic gradient is dH dr. All right, so to apply Darcy's law, so Darcy's law is equal to minus K times the hydraulic gradient times the area of flow. Well, assuming we're given the hydraulic conductivity, this is the hydraulic gradient. What is the area of flow? So if you go out to some distance r, so this is looking down in plan view, you have the radius of the well, and we're just out to some arbitrary distance. It's like this distance shown right here. At that distance, if you look at this in kind of 3D mode, the area of flow towards the well, the water is all going directly towards the center of the well. There's this band that's the height of that is the thickness of the confined aquifer, and the water is all flowing through this band. So if we can calculate the area of this, we will have this area term we need for Darcy's law. And the area is pretty easy, actually. If we can get the circumference of this band and multiply by the height, d, the thickness of the aquifer, we have it. Well, the circumference is 2 pi r. And therefore, if we just plug that into Darcy's law, 2 pi r times d for the area, here we have an equation for the flow rate. But what do we do with dH dr? We're going to assume flowing towards the well is positive, so we get rid of that negative sign. And then if we rearrange this a little bit, we bring the dr and the r terms to the left-hand side. So we have Q dr over r equal to K 2 pi d dH. And if you integrate this, you get Q times the natural log of r equal 2 pi k d h plus c. So integrating dh converts it to h, and integrating q dr over r, we get q times the natural log of r. So now, here we are once again with this constant, and the way we solve for these constants is we apply boundary conditions. So we need two sets of boundary conditions in order to solve this. And so our boundary conditions are as follows. Let me go back to the diagram. One boundary condition is right here at the well. When R is equal to RW, right at the edge of the well, the head is equal to HW. And also on the other side, when R is equal to capital R, the radius of influence, the head is equal to capital H, the initial head. So if we plug both of those into that equation, we end up with two equations. This one is RW and HW, and this one is capital R, radius of influence, and then H, the initial head. So now if we solve this top equation for C and plug it in right here and do a little rearranging, we get this equation for Q. Q is equal to 2 pi k d times H minus HW over the natural log of R over RW. This is called the time equation. THIEM is pronounced time, named after the person who initially derived this in 1906. It's been around for a long time. And so now, if you know what the head is at the well, after you've been, or if for a given drawdown or head at the well and radius of influence, you can calculate the flow rate Q. But there are a lot of things we can do with this equation. So notice you can pick other boundary conditions for this. So what if we used the radius at the well and the height of water at the well? And then for our other boundary condition, we just use RH, which is just the radius, whatever radius you choose, whatever the head is at that value. And if you do that, you now have an equation for Q that's as a function of this variable H and R. Or instead of using the radius of the well and the head at the well, if you use the radius of influence in the initial head, you can get a similar equation here. Now, why is that important? Because we can rearrange that equation and solve it in terms of H. And we can do it either with the head at the well and the radius of the well, or the initial head and the radius of influence. In either case, we have an equation which if you know what the flow rate Q is, the pumping rate, and you have these other terms, then you can use this equation to basically get the geometry of that free surface, that cone of depression. So for any radius R, you can use this to calculate the corresponding head as a function of distance away from the well, or if you use this term, you can do the same thing. So this is really useful. You can plot the shape of that potentiometric surface as you go away from at any distance from the well. You can also rearrange or write this equation in terms of drawdown. Remember, drawdown is the distance from the initial water table height down to the water table at any given point. So in general, it's H, capital H minus little h. At the radius of influence, the drawdown is 0. And at the well, the drawdown is equal to the initial head minus the head at the well after you've been pumping. And again, so if you measure the drawdown, or excuse me, so if you know the Q, you could solve this for drawdown, but now we have a simple equation relating the pumping rate and the drawdown at the well. This is often expressed in terms of something we call transmissivity, T. So you take this this term here is the hydraulic conductivity times the thickness of the aquifer. When we're dealing with confined aquifers, we often talk in terms of transmissivity T, which is just a combination of the thickness of the aquifer and the hydraulic conductivity. This equation is often used to calculate the hydraulic conductivity from a pumping test. And so if you solve this equation for K, you get this term. And notice that this H minus HW term is the drawdown at the well. And so the way this works is if you take a well in a confined aquifer, estimate the radius of influence, and then you pump it at a known pumping rate for a given period of time until it kind of settles into equilibrium or steady state conditions. Then you measure the height of, or the distance down the well to the water, which is the SW, the drawdown at the well, and plug this in and you can calculate K. So this is a really commonly used method to estimate the average hydraulic conductivity of an aquifer based on a pumping test. Just a really common thing to do for wells. You can back calculate the hydraulic conductivity. In fact, it's the most common way to measure hydraulic conductivity for a well is through a pumping test. And it's all based on this equation. How do you go about getting this radius of influence R? Well, fortunately, I will say that it's kind of a fudge factor. It's difficult to accurately estimate, or to calculate. So we use some equations to estimate that. But fortunately, remember that this is used in the equation as ln R over Rw typically. And if you look at different ratios of this, as you go from 10 to 10,000, this natural log of R over Rw only varies from like 2 to 9. So that it doesn't vary too much. You can have pretty drastically different values of radius of influence. It's not going to change the result too much. I would say the hydraulic conductivity is often a bigger unknown in terms of this, but we do have a number of equations we can use to estimate these, and this is a kind of a sampling of some of these that are more widely used. So these are just empirical relationships, semi-empirical and empirical, and it uses things such as recharge and effective porosity and drawdown at the well, hydraulic conductivity, initial thickness, and this one right here is pretty widely used, the Sykart formula. It's really simple, just a function of the drawdown at the well and the hydraulic conductivity. But you can use these to kind of estimate. And we have an exercise we do in class where we try a bunch of these and compare the results. Now, if you're a little nervous about that radius of influence, you don't trust it, if you happen to have two monitoring wells at two different distances away from the well, R1 and R2, and if you know the head in each of those monitoring wells, so you have H1 and H2, you can plug those values in at boundary conditions, and away you go. And in fact, even if you had one monitoring well, you could use the head at the well and the radius of the well for one, and then the water level in a monitoring well. So there are ways to get around having to rely on a radius of influence as well. Now, some limitations for this. It's most accurate when you have soils with a high value of hydraulic conductivity, which, if it's an aquifer, we typically do. You have to remember that K is the average horizontal K for a large region of soil. It's difficult to determine when steady state conditions develop. It might take some patience. And of course, there may be flow present which is independent of the well. The water table may be sloping, etc. Remember the assumptions we made to begin with. But nevertheless, it's still a very handy, very convenient set of equations to use for confined aquifers. Now, what if you have multiple wells? And you want to know what is the combined impact of each of these wells on the potentiometric surface in a confined aquifer. If you look at our equation for drawdown, it's H, capital H minus lowercase h, at any distance R, it's equal to Q over 2 pi Kd times the natural log of radius of influence over R. And this assumes a linear relationship between flow and the gradient. Therefore, we can apply superposition, which means if you have multiple wells, you can calculate the drawdown from all of the wells by combining the drawdown computed for each individual well. So if we have this point here and we have 4 wells pumping in a confined aquifer at a certain rate, each of which has their own pumping rate, we want to know what is the drawdown at this particular point. And from that we can get the head, of course. We take the individual pumping rates for each of those and plug them into this equation. And this equation basically means we just calculate the drawdown at this distance for the appropriate pumping rate for each of these, and we just add it up. And this is a simplified form of that equation. Instead of doing it in terms of drawdown, if you do capital H minus lower h and move capital H to the other side, this equation will give you the head at any point. So you could lay a grid on top of this and then use this equation to calculate the head at each grid cell and get a map of the potentiometric surface as a result of pumping from these 4 wells. So it's a really handy way to basically develop a model of your aquifer just using these simple equations. Now, of course, this assumes that we have a uniform thickness and homogeneous soil and so forth, but this is a really useful application of these well equations.